Okay, so now let's try to do things a little bit more quantitatively. And again, here is our barrier with the two slits in it. And I'm going to consider the pattern that's observed on some screen over here, where we're going to look for a pattern of bright and dark spots on the screen. The power per unit area that is present in an electromagnetic wave is called the intensity, and we will talk about this in another class, but for now I'll ask you to swallow that the intensity is proportional to the total electric field squared. And so that means wherever we get constructive interference, we're going to get a large intensity, meaning a bright spot. Wherever we get destructive interference, we'll have a dark spot of zero intensity. So let's think first about a point that is directly ahead of the two slits. Now, I've not drawn this to scale. This distance from the barrier to the screen, in fact, is much, much bigger than the distance between the slits. So let's label a couple of things. The distance between the slits we're going to call D, and this distance from the barrier to the screen we will call L, and we're working in the limit where L is much, much greater than D. So if I think about the paths that connect the two slits here, I'll try to draw straight lines from each slit here, and let's look at an instant in time, and I'm going to plot the electric field along this path. So let's say coming out of this slit, it might look like this, varying sinusoidally. And then because the two point emitters that are giving rise to the waves coming here come from the same wave front, the waves coming out of them are in phase. So if this one looks like this, then the one coming from the top looks pretty much the same. And you can see that because the two waves are going the same distance, they remain in phase as they get here. So right now I've shown that they're about at a zero crossing point, but as time goes forward, there will be a crest from both the top and the bottom waves that reaches this at the same time, and then a trough reaches this point at the same time, and then a crest reaches this at the same time. So the total electric field is always adding in constructive interference, and so I would see a bright spot at this point. Now let's think instead about a point that is off-center. So again, here are our two slits. I'm going to draw it slightly more realistically, so let's have the slits be a little bit closer together. And here is the screen, and let's consider a point that's off-center like this. So again, I'm going to draw lines that go to each of the two slits, and because the top slit is higher up, the path length for the top one is a little bit less than the path length for the bottom one. So we want to know how much less is it, because let's say if the situation is like this. So really, to calculate the path length, I should take the path length difference. I should take this radius line from here to here and swing it in a circular arc so that this much would be exactly equal to that much. Now let's say if the difference happens to be exactly half a wavelength. So then the wave coming out of the top one might look like this. The wave coming out of the bottom one, I haven't drawn this terribly well. Let me use green for the bottom one. If I fit exactly half a wavelength in, then you can see that the two waves are going to be out of phase, and so I'm going to get destructive interference if this extra distance is half a wavelength, I get destructive interference. So to analyze this a little bit more quantitatively, we're going to take advantage of the fact that the spacing between the slits D is much smaller than the distance to the screen L. Let me get my paper straightened out a little bit. Okay, good. So in that limit, we are going to approximate the path length difference using a triangle. So let me draw a fresh picture, and I'll try to show you what I mean. Here's our barrier. Here is the observation screen. Here are the two lines. Here is a circular arc. That's as best as I can do. And so these two are meant to be, this and this are exactly the same. But I'm going to approximate that difference using a right triangle. That is, I'm going to draw an angle, draw a line here that's at right angles to the bottom one, and I'm going to say that the actual path length difference, which is this much, can be pretty well approximated by this triangle. So that's that much. And here I've done some quantitative drawings to show you. So these are drawings to scale. When the distance D divided by L is 41%, you can see in red, that's the actual path length difference. Here's our approximation, which is just a little bit bigger. When D over L is 21%, you can see that the approximation is getting better. So you can almost not see the difference between the two. When D over L is 8%, you have to zoom in to see, and even after you zoom in, the approximate path length difference, which is shown by the blue line, is almost the same as the actual path length difference shown by the red line. And yet this is still for D over L equals 8%. In real life, D over L would be something more like 0.1% or even less than that. So this is a very, very good approximation. All right. So let's define the angle relative to the straight ahead direction to be theta. So we've got a right angle here, so that means that this angle in here would be 90 degrees minus theta. I've got another right triangle here, so this would be theta. And remember that the distance between the slits is D, so our approximation to the path length difference would be approximately equal to D times the sine of theta. Let's pause here.